Today's topic is vector-valued functions. It's a function which will take one value and give you back multiple things. So usually they write it as xt, yt. There will be a function which takes one value in and give you back a two-dimensional vector. You could also have a function that gives you a three-dimensional vector. And for some reason, it's customary to call such a function as r of t. So let's start with an example. Let's think about the following vector, which is like cosine t, sine t. I'm kind of fluctuating between two different conventions. So apparently your textbook uses this for points and this for vectors. But a lot of other textbooks just don't distinguish them because points can be considered as a position vector. So if you have any point in the space or on the plane, you can always think of the origin as the beginning point and consider that point as a vector too. So I think I began with this convention for vectors, but then I have a habit of using that. Okay, but that's not the important thing. The important thing here is that for each t, you're going to get a point on the plane. Think of this as a position vector, meaning that you're placing the origin at the origin, placing the initial point of the vector at the origin so that the endpoint is what you're given. And you know that cosine t comma sine t is indeed a point on the unit circle, right? So at every time you're going to get something on the unit circle. For example, find r of pi over 3. For that, you simply plug in pi over 3, which gives you cosine pi over 3, comma sine pi over 3. And cosine pi over 3 is 1/2, and sine pi over 3 is radical 3 over 2. And pi over 3 being 60 degrees, you're somewhere here, this point. This point right here is r of pi. Note that it's also customary to call the x-coordinate as xt and y-coordinate as yt. So let's think about the following question. B. Find Vt. And when I say Vt, I mean the velocity. And the reason I'm asking that question is because when I see this function, I'm really thinking of this as like a particle that's moving on a path at different times. Okay, so when t increases, it goes around the circle counterclockwise. So because it's moving, you can definitely talk about this velocity, right? So if I take, to find the velocity, what do you have to do?
Take the derivative.
Take the derivative, right? So we take the derivative. And that means you get negative sine t, comma, cosine t. Okay. Part C, find angle between RT and VT. And the answer is, we know that the solution, the cosine of the angle between is, you have to take the dot product of the two and divide it by their individual sizes, right? But if I calculate the RT dot VT, what's that? That's cosine T sine T dotted with negative sine T cosine T. And because dot product is obtained by taking products of coordinates, and then you have to add. Yeah, here it's cosine times negative sine, but I pull the minus in front. And if you look at this, these are exactly the same, but this has a minus, so they add up to 0. Okay, if the dot product is 0, what does that tell us about the angle?
Perpendicular.
Perpendicular, because if the dot product is 0, then this numerator will be 0. That means cosine of theta is 0. When is cosine 0? When theta is 90 degrees. Okay, so this says the angle between is 90 degrees. Well, something like this is quite familiar. So let's WT R sine WT. So here, my function has two constants, R and W. And this is really omega. So the Greek letter omega, which is really the vowel O, not W, looks very similar to the English letter W. So there's definitely a confusion there, but I'm just going to say W because people read it as W anyway, but it's really omega, okay? Greek letter omega. Okay, so let's think about what this function describes. Okay? When t is 0, what do you get? Cosine 0 is 1. 1 times r is r, okay? When t is 0, sine 0 is 0. And 0 times r is 0. You should definitely remember these two pictures. Okay, so this is sine graph. This is cosine graph. So cosine 0 is 1, sine 0 is 0. Make sure that, don't try to memorize the values, rather memorize the picture. Yeah, so this is like 360, so you can see that sine 90 is 1, whereas cosine 90 is 0. You can read off those values just from this picture, okay? So when t is 0, you're at r comma 0. Okay. Now, when omega t is equal to pi over 2, in other words, when this is 90 degrees, when this entire thing becomes 90 degrees, then I just said that cosine 90 degrees is 0, whereas sine 90 degrees is 1. So 0 times r gives you 0, 1 times r gives you r, so you're at 0 comma r. Where's 0 comma r? It's here, right? And as time went by, this is how it moved. And because we just did a previous example where this was 1 and this was also 1, and we got a circle, you can kind of see that what this r does is it just makes the circle larger to be radius r. And what w does is that if you put a big number there, it just rotates around the circle faster. Because if you put like 10, then even small increase of t is going to make a small change of angle. So it just makes this thing go around the circle faster. Do you have any question about this? Does this make sense? So try to make sense out of this function. It's, when 0, you're here. When it's pi over 2, you're here. When wt is pi, you're here. So you end up going around the circle of radius r. Okay. So now if I want to find the velocity, I have to differentiate it, which gives you negative r omega sine omega t and r omega cosine omega t. Okay. Tell me where this omega came from. W, yeah.
You took the derivative of the cosine.
Yeah, what happened?
You have to multiply out the a side.
What's that rule called?
Chain rule.
Chain rule, yeah. So the chain rule was applied to give you the omega, W. And then, how do I find the speed if I know the velocity?
Magnitude.
Magnitude, yeah. So speed is going to be, see, it's customary to just put v, the same v, but without the arrow on top. So that's the magnitude of this. And that's going to be square root of negative r omega sine omega t squared plus r omega cosine omega t squared, which becomes r squared omega squared sine squared omega t plus r squared omega squared cosine squared omega t. Minus went away because if you square minus goes away. And then you can factor the r squared omega squared out, and you get sine squared omega t plus cosine squared omega t. Okay, what's this equal to? Sine squared plus cosine squared. 1, right? Sine squared plus cosine squared is 1, therefore you get square root of r squared omega squared, which gives you r omega. Okay. So what you see is that because omega is multiplied to t, and this is the angle that you're rotating, right? Bigger omega makes it go around this faster with bigger angles. Okay. But then if you increase r, and so what I'm trying to say is that once you have that intuition, you can see that this is what's known as the angular speed. Because it makes the angle increase faster. But if r is bigger, what happens? If your arm is, if you rotate this much compared to this, if the same angle is being changed, right? the bigger radius means it moves long for a further distance, right? So that's what this formula is saying. Say V is equal to RW. The longer your arm that's rotating, the faster the velocity will be with if the angular speed is the same. Okay. All right, now let's look at the acceleration. How do you get acceleration? Take the derivative of the velocity, because acceleration is the rate of change of the velocity, right? So you take the derivative of this guy, we already have it, and that's going to give you negative r, another omega will come out, so it's going to be r omega squared. Sine differentiates to cosine. Cosine differentiates to negative sine, so it's negative r omega squared sine omega t. And once again, you get this omega, extra omega from the chain rule. It's the same story if you took the norm of a t, this gets squared, that gets squared, but you end up with cosine squared plus sine squared at some point if you factor the r omega squared out. Yeah. Or maybe a quicker way is to do the following. You can rewrite this as r omega squared negative cosine omega t negative sine omega t. Then the norm of AT will be just r omega squared times the norm of this other guy. Because this is a positive number, and if you take a vector and you multiply by any number, so I'm trying to talk about this formula. If you have a times some k times a vector, the norm of k times vector is same as k times norm of v, assuming the k is positive or zero. Okay? Any multiple of a vector, you can bring that k out. That's a property of the magnitude. So that's what I'm doing. Taking the norm of this entire thing, because this is positive, you can move it outside. And now all you have to do is you have to take the norm of this guy. Well, what's that? That's this square plus that square. That is cosine square plus sine square, which gives you 1, right? So this is going to be a unit vector. It'll be a 1. You get r omega squared. Okay. Some more observations. If you do RT dotted with VT, what do you get?
90 degrees.
Yeah, you get 0 because we did the calculation like that a moment ago, but if you did it, you'll see that you get negative r squared omega squared cosine WT sine WT plus r squared W squared sine WT times cosine WT. And if you switch these two around, they're the same thing with the minus sign, so it's 0. So that says RT and VT are perpendicular. What can you say about the direction of the acceleration? What's the relationship between this one and this one? Now, if you remember from physics 1, you probably have some intuition about the,
Isn't the negative sign in a different direction?
negative means it's the opposite direction, right?
Yes.
So what the acceleration is saying is, see, at every point, RT is this one. This is RT, right? But acceleration is exactly in the opposite direction, because if you look at it, this is R times cosine WT sine WT, whereas this one is negative R omega squared times cosine WT sine WT. So you have the same direction vector, but one is positive, the other has a negative multiplied. So you have the opposite direction. Okay? Now, we all know from Newton's laws that F is equal to m times what? M times A. So what does that mean for the direction of the force?
Direction of acceleration.
It's same as the direction of the acceleration, because mass cannot be negative, right? So positive mass, the direction of the acceleration is that. Okay. Furthermore, because I have here that V is equal to RW, if I solve this for W and write W equals to V over R, you stick it in here, you get the following equation that some of you may remember. A is equal to R omega squared equals to R times V over R squared, which is equal to R times V squared over R squared, but one of the R's cancels, so you just get V squared over R. Therefore, F, not the vector, but the magnitude of F, right? This is the magnitude of acceleration. F equals to ma, and A is this, so you get m times V squared over R. How many of you remember this from physics? You've seen this in physics 1, right? Yeah. And we've basically proved that formula just by using that. And because of that, here's my challenge to you. Forget everything here except this one. Let's say you're given this formula. Okay. And just from this, just take a white blank paper, write this on the top, okay, and try to derive this formula without looking at anything. Just do the, it's simple. All you have to do is differentiate once and take the norm, see what the relationship is, okay? Differentiate twice, take the norm, see what the relationship is, and then you just put the two together. See, we just found out that A is equal to RW squared, and V is equal to RW. Put them together, you get A equals to V squared over R, and therefore F equals to mv squared over R. That's what it is. Okay? Now, in terms of physics, what this is saying is, if you have a constant velocity motion that's going circular, we know it's constant because I said R and W are both constant, so the velocity is constant. Sorry, you can't say constant velocity means it's a straight line. Sorry, yeah, that's wrong. Constant speed motion, that's a big difference, right? Yeah. So if you have a constant speed motion that's going circular, right, then that means the direction of the force must always be going towards the center of the circular motion, okay? The velocity will always be perpendicular to the acceleration, okay? You have a constant acceleration going perpendicular. That's what's happening. Okay? So those things are something that you may have tried to understand from a physics textbook, but I don't think, I never can understand physics book, textbook explanation. Because what they're trying to do is they're trying to explain both of these, the fact that force is towards the center. What's that called? Centripetal force, right? Yeah. Centrifugal will be the opposite, I think. Yeah.
That's how it.
Huh?
Centripetal.
Yeah, it's centripetal. Yeah. So centripetal force is always points to the center, and the fact that F is equal to m times v squared over r. I always try to read that part, and I can't understand what they say. Yeah, and they're all probably trying to mimic this explanation without using calculus, so that's hard. Yeah. See, math makes things easy. Yeah. Once you know enough math, then things that you see in physics just make sense. Yeah, I think that calculation that I just showed you should be an experience for every engineer. Anybody who's doing engineer should be able to experience this for at least once. Taking this one and without looking at anything, just take the derivative and do the calculation, and you get the F equals to m v squared over r just on your own. Okay. Now let's talk about 3D curves. Here's an example. RT equals to t comma cosine t comma sine t. So that's a 3D curve because at every point in time you have a point in space and the particle is moving, so the trajectory of that particle is going to give us a 3D curve. Let's try to understand what this does. We've already seen that this part makes things go round and round, right? So if this is x, that's y, z. And the very first place that this particle is placed at time t equals 0 will be when you plug in 0. What's cosine 0? 1. Sine 0? 0. If you plug in 0 to t, you get 0. So you get 0, 1, 0, so which is right here. Okay. Now, if you didn't have the x-axis, then in the yz plane, this is a circular motion, right? So let's say you're here, right in front of x, so that you don't really see the x-axis. It's like coming towards you. Okay, the x-axis is coming towards you. Okay, and here's y and here's z. Okay, and then that means you're not going to notice that t is changing, right? And you let t go increase, then what's going to happen? It's going to go round and round, right? But at the same time, unbeknownst to you, the t value is increasing, meaning that it's moving in the x direction, right? So you watch that going round and round, and at some point, it hits you, right? Both figuratively and literally, right? Because the particle literally hits you, and at the same time, when it hits you, you realize, oh, there's a t direction, x direction that's moving, right? Yeah. So can you picture the actual trajectory? What's going to happen? It's not. Just like that. Let's see here. Yeah. So it's like this. Okay. That's what's happening. Such a curve is known as the helix. Not the helix, a helix. Okay, so the picture for this is this is a helix. Now, what can you do with that? Well, one of the questions that you can ask is A, find a tangent line, the equation of the tangent line. I mean, that's what you've been doing a lot in Calc 1, right? You're given a function, you have to find the equation of the tangent line, right? So find the equation of the tangent line at t equals, so let's say, 2 pi over 3. Since pi is about 3, so this is about a little more than 2 points on it. Okay, so how do you do that? Well, 2 pi over 2 is somewhere here. So here's the x-axis, here's y, here's z. So it's doing this, and at some point here, at 120 degrees, you have some line that you want to draw that's tangential to it. Right? But then you remember for the line equation, what do you need to get a line equation?
Slope.
We don't say slope in 3D, instead what do we say? For lines in 3D, we don't have slope, instead what do we have? What kind of vector?
Unit.
Not the unit vector. Direction vector. You need a direction vector, right? Yeah, so to get a line equation, you need a direction vector. What's the other one that you need? You need a point. So it's just like the point slope form that you have in 2D. We have the, if you have a direction which is in place of the slope and you have a point, then you have a line equation. So, well, there are two types of line equation, but let's go with the symmetric one. It's x minus x1 over a, y minus y1 over b, z minus z1 over c, where a, b, c is a direction vector, and x1, y1, z1 is a point on the line. Okay, so how are we going to get those? How are we going to get A, B, C? Any ideas? How can we get the direction of this line? I mean, if you look at the picture, it's going like that. And then, so we need a vector that's tangential to this curve. That's to be that. Yep.
Do you plug in 2 pi over 3, and that gives you the point, and then you take the derivative of the line,
Yeah.
and then that gives you the direction vector?
Yes. You learned in Calculus 1 that if you differentiate, you get the slope of the tangent line, right? Same thing here. If you differentiate the function, you get the velocity vector. But anytime you have something that's moving, the velocity vector will always be tangential to the curve, right? You get that? Okay. So to get A, B, C, you first have to find the velocity vector, which is the derivative. And then use t differentiates to 1, cosine differentiates to negative sine t, sine t differentiates to cosine t. So this is the velocity at every point for t, but we're specifically looking for the velocity at t equals to 2 pi over 3. So we're going to look for vt evaluated at 2 pi over 3. So that's going to be 1 negative sine 2 pi over 3 cosine 2 pi over 3. And that's going to be 1. Let's see, that's going to be negative or equal 3 over 2, negative 1/2. So this is your direction vector. And if you want a point, the curve and this tangent line is going to meet at this point. So you just have to know where the particle is when t is equal to 2 pi over 3. So r at 2 pi over 3 is going to be 2 pi over 3, comma cosine 2 pi over 3, and sine 2 pi over 3. And that's going to be 2 pi over 3, comma, negative 1/2, and radical 3 over 2. Okay, so we have both ingredients. We have the point from there and direction vector from here. Therefore, the answer is x minus 2 pi over 3 over 1 equals to y minus negative 1/2 over negative radical 3 over 2 equals to z minus radical 3 over 2 over negative 1/2. That's the answer. Yes?
For the r, all we did was just take the derivative of.
No, r is the original function.
Okay.
Yeah, and I'm just evaluating it at 2 pi over 3 because that gives me the location of the particle that's moving with each t. When t is 0, the particle is here. And as you increase t, it's moving. And when you plug in 2 pi over 3, the particle is right here. Now, that is exactly the point where the line is also passing because the line is tangent to this point at 2 pi over 3. So evaluating 2 pi over 3 to this function is going to give you a point on the line. Since we need a point and a vector, we got the point just by plugging in 2 pi over 3 over here. Okay? Thank you for the question. I think that question clarified the core of this to a lot of people in this room. Okay? All right. Any other questions? All right. So now the second question that could be asked is find the arc length from t equals to 0 to t equals to 2 pi over 3. So in other words, we're looking for this arc, that length. Well, now, if you just do math, sometimes that's not enough. I mean, I talk about physics a lot because if you have the physical intuition, math is easier to understand. So they're like complementary. You really want to know physics and math at the same time because knowing one will help you understand the other better. So the reason I'm saying that is because you see, if you integrate velocity with respect to time, what do you get?
Acceleration.
No, the acceleration is the derivative of velocity. If you integrate velocity, what do you get?
The distance. Yeah.
Not exactly the distance, you get displacement. Okay. But if you integrate speed, what do you get?
You get distance.
You get the distance traveled. Now the important distinction between these two is that one is a vector and the other is a scalar. See, if you have time t equals to 0 and time t equals to 2 pi over 3 here, and you took this velocity here and you integrated this with respect to dt, just like that, from t equals to 0 to t equals to 2 pi over 3, then what you're going to get is difference between these 2 points because, okay, so let me try to explain this. When t equals to 0 and t equals to 2 pi over 3, vt is the velocity, then the antiderivative of vt is rt, isn't that right? So you get rt as the antiderivative and you're plugging in 2 pi over 3 and pi over just 0. And that means you get r at 2 pi over 3 minus r at 0. Now, what's r0? It's this point, right? What's r 2 pi over 3? It's this point. So you're doing a these are both vectors, so if you subtract them, you get another vector, which is this vector. This vector is called the displacement. It tells you how much the position changed. Okay? That's the displacement vector. Another way to think of it is like, let's say I just came back from the library, and then while teaching I realized, oh, my watch, my Apple Watch or something, it's important, I can't lose it. So I say, class, do this exercise, and I run to the library, get my watch, and I come back, okay? What's my displacement?
Same.
0, right? It's a 0 as a vector, right? Well, what's my distance traveled? It's twice the distance of here to the library, right? That's the difference between these two, okay? Displacement doesn't care about what happened in between. It just cares about the beginning and the end. And it's a vector that has the initial point at the beginning and terminal point as the final. Okay? That's what displacement does, as you can see. However, if you took the speed, by the way, is the norm of the velocity, right? Then that's a scalar quantity. It tells you how fast you're running, right? As you're going, okay? And it doesn't care about direction, okay? If I'm running to the library, it just records how fast I was running. At some point, after I take my watch, I'm going to turn back. Change of that direction, it doesn't care. It will just continually add up all these velocity, speeds at each time, and you add them up, and what do you get? You get the entire arc length. You get the arc length. Okay. Because that's the distance traveled. Of course, so here's another thing. A moment ago, I was complaining about physics textbook because it's trying to talk about this circular motion without calculus, and it's harder to understand that way. Yeah. Now, if you open up a calculus textbook and see how you get the arc length, it's also not so enlightening. If you know the physics, it's obvious why that should be true. Okay. So let's now use this as a formula to calculate the arc length. In our case, what is this? This is 0 to 2 pi over 3. Oh, by the way, yeah, I wrote down ds here. This is wrong species. Okay. So, norm of VT dt is often known as, this is often known as ds. Okay. And the way you think of it is like s is like the arc length, and ds is like the very small change in that. If I have to explain at some point, I'll explain this notation, but let's not worry too much about that one. But here's our formula. That's all we have to do, okay? So what's the norm of VT? We have the VT somewhere. Did I erase it? Okay, I just erased it. Okay. But I know that the derivative of t is 1, and derivative of cosine t is negative sine t, and then derivative of sine t is cosine t, and you're just squaring each one of these components, and you take the square root. That's what the norm is, right? You have to do dt. Oh, but wait, this is sine squared, that's cosine squared, they add up to? 1, and then you have 1 squared, 1 plus 1 is? 2. So you end up just integrating from 0 to 2 pi over 3, just square root of 2 dt. And constants are very easy to calculate. I might even be able to fit the calculation here. But this square root of 2t, and you're plugging in 2 pi over 3, and then 0. Therefore, if you plug in these things, you get square root of 2 times 2 pi over 3 minus 0. So the final answer is the arc length is 2 radical 2 pi over 3. It's a rather strange answer, but that's what it is. Any Calculus 3 textbook, when they ask these things, they usually work with the helix because it's easy to integrate. If you have some other innocent looking functions, often they give you intervals that you can't do. Okay. Right. So let's have some idea of what this is. It's at t equals to 0, you're at the origin. And as you increase t, all three coordinates are increasing, right? Now, if it's all increasing like t, then it will be straightly coming out this way. Here's x, y, z. But when t is less than 1, then which is the largest if t is 0.9? T or t squared or t cubed? If t is 0.9, t squared, t cubed. T is the largest, right? Yeah. 0.9 cubed will be, what is that? 0.729. Okay, so it's lower than 0.9. Okay? So you see that x coordinate is the largest, so it's somewhat turning towards to the x coordinate in the beginning. But then after it touches 1, 1, 1, and then it will turn the other way because now these are increasing much faster. So it's some weird curve that when t is 0, you get 0, 0, 0, and t is 1, you get 1, 1, 1, which is somewhere here, but it's bending somewhat like this. Then, yeah. It's a bit hard to imagine, but at some point when t is 2, you're at 2, 4, 8, somewhere here, up there, I don't know. Yeah. And you're trying to find the equation of the tangent. So let's just say it's something like this. It's grossly misrepresented, but let's say this is a curve, and that's where t equals to 2 is. And the first question is asking you to find the equation of this tangent line. And you have derivative of rt giving you the velocity, which is 1, 2t, 3t squared. r prime of two is going to give you 1, 4, and 12. That's going to be your velocity, which is going to be your direction vector of this blue line. And then if you evaluate r at 2, it's going to give you 2, 4, 8. So the equation of the tangent line will be x minus 2, y minus 4, z minus 8 for the 2, 4, 8, and then you put the direction 1, 4, 12 in the denominator, set them equal. So that's the answer to part A. Now, what's a normal plane? I haven't told you what it is, but can you guess what it is? What's a normal plane at this point? Normal means what?
Perpendicular.
Perpendicular, right? Yeah. So normal, orthogonal, perpendicular, right angles, all mean the same thing, okay? Yeah. But normal is usually used when you have a two-dimensional thing, a surface, and a linear thing, line-like thing, okay? So that's normal, that's what it is. So here in part B, you're looking for a plane that's perpendicular to this curve, okay? Now let me ask this question. For a plane equation, what do we need? What do we need for a plane equation? Huh?
Direction vector.
No, you don't say direction vector for a plane. Plane equation requires what?
Normal vector.
A normal vector, right? So for part B, remember the plane equation in 3D is a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals to 0 with x1, y1, z1 as just a single point on the plane. And then ABC is this vector that's perpendicular to the plane. So you choose any line that's inside this plane and it will always be 90 degrees. So such a thing is called a normal vector. And now that looking at the picture, you see that, oh, the velocity will be actually normal to the plane because the curve is normal to the plane, right? So now we can use ABC to be 1, 4, 12, and 2, 4, 8 could be x1, y1, z1. So the answer to part B will be 1 times x minus 2 plus 2 times x minus 2, 4 times y minus, no, sorry, I'm messing this up. 1 times x minus 2, 4 times y minus 4, plus 12 times z minus 8 equals to 0. Okay. So that gives you a plane equation. Okay, now this part C was actually to demonstrate why these questions of arc length often become ugly. That's why I said leave it in interval form. See, I have the derivative here, right? Because I know that the arc length, usually you write it as S. S is equal to norm of V dt. And from 0 to 2, that's what we're doing. So we need to integrate square root of this one. 1 squared plus 2t squared plus 3t squared, and then dt. And that gives you 0 to 2, square root of 1 plus 4t squared plus 9t to the 4th dt. Now, unfortunately, this integral cannot be done by hand. There is no easy way to do this integral by hand. So that's it. You can't go any further. Yeah, so all the methods that you learned in Calculus 2, like integration by parts, substitution, partial fractions, trig substitution, you name it. You can try everything. It's impossible to integrate. So all you can do is you can just plug this into a calculator and find the approximate value. That's all you can do.